Hello everyone, welcome back to Calculus 3, and we are in the topic of equations of planes in section 2.5. And for the purpose of this class, I'm not going to give any explanations how we generate the equation of plane. But anyway, I'm just going to present this as a result. To determine the equation of plane, we need to have a point, a given point, and a normal vector. The normal vector of a plane, it is a vector perpendicular to the plane. And then if that is the case, the equation, it is arranged as the following. A times parentheses x minus x naught parentheses plus b times y minus y naught plus c times z minus z naught. And actually I need to make a correction here. This should be 0. This should be 0. This should be 0. Okay. So simply put, to write out the equation of plane, we need to have point and a normal vector. And how about, let's take a look at the example. Actually, this is the one from the textbook. Checkpoint 2.47. I'm not sure how if you read this problem and find an equation of the plane containing two lines. That's all about it. And also, as I'm saying, you may want to use two lines. Well, I lost my video for now, video of myself for now. I say you may want to play by yourself and to see if you can visualize how the plane would look like. I'm having two pens in my hand and I'm seeing I can visualize a plane from two lines. Okay. One thing you want to make sure here is passing two lines. Those two lines, they must intersect to form a plane. Okay, the two lines must intersect. So as a solution, I said that first we try to find out the intersection of those two lines. In this case, I hope it's easy to understand. Basically, what I did, I just put the result in equation 1, in line 1 to line 2. Because the equation 1 is simply says we are having a line x equals negative y equals z. So I replaced x with negative y. I replaced everything into y. And the z also is at negative y. So what I'm having here is the second equation of the line. It just tends to be an equation, actually two or three equations. All three equations tend to be with a single y. And indeed, we do have a solution for y here. And I believe y should be negative 1. Y should be negative 1. Then because y is negative 1 from here, and then we go back to the equation 1, line 1 here, which means x is 1 and z is 1. And indeed, you can check, double check, for verification purpose. Put all those three values back to equation 1 and equation 2. They both work, which says clearly those two lines, they do intersect, which means there is a plane containing those two lines. Okay, and then the other issue, you may want to look at the requirement for us to write out the equation of a plane. We need to have a point, I suppose the intersection is the point we just got. And then the normal vector, how do we get the normal vector? Well, this part, it does require a little bit of abstract idea. How do you think about the arrangement in the three-dimensional space? Okay. What I'm seeing here is a line, the plane we are looking for will have to pass those two lines, line 1 and line 2. And the normal vector, put in a simple way, it is a vector perpendicular to the plane. And you think a little further to see if it will make sense. Use a pen and a piece of paper and to see if it will make a better sense. And when you have a vector perpendicular to a plane, indeed you can say that a vector, it is perpendicular to any line in that plane. So what I'm seeing here is we are having two lines in that plane. So the normal vector will have to be perpendicular to both lines. Do you know how we find a line, a vector perpendicular to both? Is it the cross product? Okay, cross product, it is the right answer. So this is what I wrote next. Note for this equation 1, and I say there's a directional vector. Directional vector of a line, it is a vector parallel to the dotted line. And I'm seeing the directional vector, it is 1, -1, and 1. And if you are not sure how I get the directional vector, you may want to read the notes, the previous part. Okay, we do have the discussion for the equation of a plane, and there is a symmetrical equation. I'm seeing the equation given for line 1, line 2. Each it is in the symmetric form. So I'm getting there's no denominator. Indeed, you should consider this as x over 1, y over -1, z over 1. So I'm having the directional vector as 1, -1, and 1. And similarly, for the second line, line 2, I'm having the directional vector as 2, 1, and 1. So we are having two directional vectors. And as I just said, the normal vector of the plane will have to be perpendicular to those two. So indeed, the normal vector can be found using the cross product of those two vectors. I say the normal vector is ABC. Indeed, it is a cross product of the directional vector for line 1 and the directional vector for line 2. And then for the calculation of the cross product, this is really what I always do. I always remember the cross product in the matrix fashion. The first row, it is always ijk. The second row, it is the components from the first vector. The third row, it is the components from the second vector. And then the next line, well, the reason I'm using the matrix format, because I know it can be reduced into 2 by 2s. So the I component, you cross out the row and the column where I is. So I'm having a 2 by 2 matrix. Similarly, you do that for J and the K. And again, for the J component, there is a minus sign there. And then let's try to finish all the calculation. Along the I component, I'm having this matrix. The determinant would be, I believe it should be all right, -1 minus 1, -2. And then for the J component, that's 1 minus 2. Determinant is -1, but combined with minus sign in the front, so it tends to be +1, plus J. And for the K component, we are having 1 minus -2, 1 plus 2, that's 3K. So the normal factor A, B, C are -2, 1, and 3. And now look at the problem we are working on. It is to find out an equation of the plane passing through both lines. And first we got a point with my point here. Actually, this is the point, right? And indeed, we could maybe denote this as x naught, y naught, z naught. Okay. And then we got the normal vector, which is right here, a, b, c. Then finally, according to the formula we provided in the beginning, the equation of a plane passing through a point with the normal vector, it turns to be such. Hopefully I get all the numbers correctly. -2 times x naught is 1, y naught is +1, and the j component here is 1. So I believe I'm all right. and you helping me double check if I got all the numbers and the arrangement correctly. So this is the discussion of section 2.5. Two topics. It's about the equations of lines and equations of planes. And for now, I want to say we are done with both. Thank you for watching.